Good morning, good afternoon, good evening to all of our attendees joining us today for this latest Data Science Central webinar. This is Bill Voorhees, your host. I'm the editorial director with Data Science Central and also chief data scientist for Data Magnum. I'd like to start off our event today by thanking MapR and Think Big, a Teradata company, for sponsoring today's event. Both companies have been longtime supporters of the Data Science Central community, and we're honored to have them sponsoring our event today. I'd also like to take this opportunity to mention and show our appreciation for some of our recent sponsors, including Tableau, Microsoft, Hortonworks, Oracle, and IBM, to name just a few. Past webinars are available on demand at datasciencecentral.com. If you haven't had an opportunity to view them, I encourage you to take a look. They provide very useful insight into a wide variety of topics of interest to our data science community. Today's webinar is entitled, When is the Right Time for Real-Time? Architectural Best Practices for Hadoop. Now, before we begin today's seminar, I'd like to review the format briefly. Today's webinar is an hour long. We have two panelists that I'll introduce in just a minute. There'll be a 10 or 15-minute QA following the presentation, and this event is being recorded and will be available on datasciencecentral.com later this afternoon following today's live event. I'd also like to encourage our attendees to provide questions throughout the presentation. We'll be reviewing them and presenting them on your behalf during the Q&A portion of today's event. I'm very pleased to introduce today's speaker, Steve Wooledge of MapR and Bill Kornfeld of Think Big. Now, Steve is Vice President, Product Marketing for MapR and responsible for identifying new market opportunities and increasing awareness for MapR's technical innovation and solutions for Hadoop. Steve was previously Vice President of Marketing for Teradata Unified Data Architecture, where he drove their big data strategy and market awareness across the product line, including Apache Hadoop. Now, Bill is Director of Research and Development for Think Big and has more than 3 decades of experience designing, architecting, developing, and managing the development of high-performance server architectures. He's been working with Hadoop since 2008 and has been Director of R&D at Think Big for the last 2 years. In recent years, he's worked on a wide range of applications in the event analytics space, spanning both engineering and data science. Thanks for being with us today, Steve and Bill. We're looking forward to your presentation. Real-time processing is an important part of your Hadoop architecture, but is it always the best approach to analytics? In today's webinar, with experts from MapR and Think Big, we'll delve into the decision-making process around Hadoop real-time and batch processes. You'll learn the ins and outs of low-latency design for analytics, and as we'll see how these designs get implemented in the real world. In today's webinar, you'll learn useful design patterns for building your Hadoop stack that best serve low latency requirements, pitfalls to avoid when choosing your real-time processing option, real customer examples highlighting decision-making processes for both real-time and batch processing. Now, before we begin today's presentation, we'd like to ask the audience to participate in a short survey. These help us give a clearer picture of who's with us today and some of the issues that you may be experiencing in your professional lives relating to real time. So here are our survey questions. What is your greatest challenge in terms of real time? Data ingestion, stream processing, making immediate decisions on event data, analytical response time, queries that take too long to come back, enabling faster decision making with dashboards and alerts, or I have no challenges with real time, batch is fine for me. So if you take a minute and select the one which most clearly describes your current situation and hit the submit button, I'll give you just a second to respond. Okay, moving on, and thanks for participating in today's polls. Here are the results. And it looks like in the lead is analytical response time, queries take too long to come back. And you can see the results for the balance of the questions. And about 90% of you said you do indeed have a problem with the way real-time is currently being handled. So, Steve, Bill, with that, I'm going to turn it over to you. You can begin as soon as you're ready to go.
Okay, thank you, Bill. This is Bill Kornfeld from Think Big, and as Bill said, we're going to talk to you today about when is the right time for real time, in particular how you decide whether you want to use real-time or batch architectures for solving particular problems, and sometimes the answers are a little surprising. So we're going to go over today, first the question of what does real-time mean in the context of big data, and then we're going to talk about design patterns for implementing real-time in the Hadoop ecosystem, and also design patterns for batch systems, and how you decide whether you want to use real-time or batch. And then I'm going to talk a little bit about kind of event analytics at Think Big. It's a major effort on our part to develop infrastructure for processing events from multiple channels, such as clickstream data, ad web click data, etc. And I'll pass the baton to Steve, who will talk about some specific customer example applications that they have done at MapR. And last, we'll finish with a Q&A. Okay, so the first question is, what does real-time mean? And this is a very high-level block diagram of information going in and out of a data, some sort of data store. We're going to be talking about Hadoop today, but this is kind of a more general formulation. So we have data in from some source. If data doesn't come in, you can't do anything. And then we have information coming out. Information coming out can actually come out in two ways, either with push or with pull. A push architecture is where the blue box takes information and pushes it to, say, a web browser or to a system that can otherwise kind of act on the results of the data coming in. And a pull system is one in which the user through some action gets information out kind of when they need it. So in whether push or pull, what we're going to define real time is as looking at the latency from when information kind of enters the data store to where information comes out, and we will consider an architecture real time if the latency there is a second or so. So for example, if a message comes in and then you query the data store and the information you get out reflects the new information coming in, and that whole thing happens in a second or two, then we would call that a real-time architecture. But one in which data is constantly flowing in, but it may take a minute or two to process it, to kind of get the analytics to represent the new information coming in, then we consider that a batch architecture. Okay, and one of the reasons that we've come to this definition is if you look at the tools in the Hadoop ecosystem, the ones on the left are kind of the more traditional ones. They, probably when you first heard of Hadoop, those were the ones that were there, the only ones that were there. When I started working with Hadoop in 2008, thereabouts, there was MapReduce and Pig, and Hive hadn't yet come into being, but it did shortly thereafter. So these are the batch technologies, and kind of a modern Hadoop 2.0 system. You can use these if you want kind of latencies of a minute or two. These technologies work just fine. But if that kind of latency is not acceptable and you need latencies down to a second or two, then the tools on the right are the ones that you would kind of make use of. And again, some of them are, they kind of divide into two classes. There are the streaming technologies, such as Spark Streaming and Storm. And then there are the SQL on Hadoop technologies, the modern ones like Presto, Drill, and Impala, which by keeping everything on RAM and making use of kind of many core in the Hadoop system to answer questions, kind of working simultaneously, can achieve very, very low latencies on queries. Okay, now one very common application in a Hadoop system, or really any information architecture, is kind of storage and retrieval of information. And we're going to divide it into two classes. There's atomic and aggregate storage and retrieval. And roughly, atomic retrieval is one in which a single message comes in, and then you make a query, and you're going to get the information about that single message. And I've got some examples here from an application we did in kind of medical information processing, where one example would be prescription records. So an individual is, say, prescribed penicillin, and that information goes in, and then you can ask a question about kind of what prescriptions did that person get, and you will get you will basically get records of the individual prescription for penicillin. So that is atomic retrieval. Aggregate retrieval is where there's a one-to-many relationship between the information coming in and the information going out. And so an example of an aggregate query is how many prescriptions for penicillin were given on June the 9th, 2015. Okay, so with atomic retrieval, you can ask the question, should this be batch or real time? And the answer is it could be both. Both would make sense. An example of a place where you'd want it to be real time is if a doctor kind of went up to the information retrieval system and wanted to know what prescriptions have been given for this person right now. And if there's a few-minute delay after the information comes in, and it's an emergency or situation, then the doctor may not have information about the latest prescriptions and might make a mistake. So case one is one where you would want a real-time architecture. Case two, say students are completing SATs, and as they're completing it, the information goes in. Well, if there were a few-minute delay in getting that information, it would be no big deal. So case two is a case where you could use a batch or a real-time architecture, but batch architectures are generally much more efficient. And so if that's all you're doing, you'd probably stick with a more traditional batch architecture. Okay, now with aggregate retrieval, it is possible to have both a batch and real-time versions of the aggregate retrieval, and we're going to discuss kind of what they might mean. In some cases, certain kinds of aggregate retrieval only make sense in batch, and I'll show you some examples of that coming on soon. So that if you had a real-time architecture, you could in some cases process the data in real time, but it's not going to do you any good because there is inherent delay in the meaning of the aggregate. Okay, so aggregates where instantaneous real-time meaning makes sense includes sums and counts. So if you were implementing say a clickstream information application for an e-commerce site, and you wanted to know how many dollars of revenue have we earned so far today, you can imagine a counter on the screen kind of continually incrementing as new sales come in. And there may be value in having the very, very latest data so that you know how many dollars you've earned up to the current second or two. But if you wanted to know if you wanted to know, kind of how many prescriptions have we written today, say you were managing the pharmacy and you wanted to make sure you had sufficient stock, then that's another case where kind of instantaneous values may have, instantaneous information may have some value to you. Okay, let's look at some cases where real-time kind of aggregates may not make sense. And a very, very common case, particularly when you're doing things like event analytics, are ratios. What you want to know is, say, the click-through rate on an ad. And so if you look at the picture below, you'll see the blue dots represent the kind of number of times the ad was shown to a particular, to a customer somewhere on the internet, and the red dots represent times that clicks were made. And it is a ratio. And so what you need to do is, in order to get a value of it, you need to take kind of the number at the top, the number at the bottom, and you need to divide them. And so what is the value of that now? Well, the value of it now really can only make sense if you look at some prior history back to some point. And so necessarily, this is an aggregate which is looking back in time. Don't know how far back. It kind of depends on how many of the blue dots and how many of the red dots it takes to get statistical significance. But you're always looking back in time, and if you're looking back in time, kind of a batch architecture which kind of counts the blue dots and the red dots, say, every minute or every 2 minutes, and presents a ratio may give you just as much information as one that is calculating it on the fly as the information comes in from some historical window, kind of begun from the current time to some point in the past. Okay, here is a case where an aggregate value has actually no instantaneous meaning, but has a very, very well-defined batch meaning, and that is unique user counts. Now, what is a unique user count? If you look at kind of web analytics applications, they will typically tell you for a given period of time how many different users came to your website. And so the red dots represent kind of, different times that users kind of viewed pages on the website, and you see that a number of the names kind of repeat. And what you want to do is you only want to count each name once, regardless of the number of pages they looked at in the time period. So it's clear how to kind of count this in a batch way. You pick a period of time, you see how many unique names there were, and that's the value of the metric for that time period. But what sense does it make to do this instantaneously? Well, at the current moment, there is, it's simply undefined. All you know is historical values of that metric. At the current moment, it has no meaning. Okay, here's another case where you could use kind of real-time analytics, but batch analytics is vastly kind of more efficient. And if you imagine, and this is kind of OLAP applied to kind of web analytics data, where you have events coming in, and then you can tell from the event whether the person is on a PC or whether they're on a Mac, and you may be able to tell, because they're registered users, whether they're male or female. And so you want to know, for particular metrics, what is the value for males using PCs, females using PCs, et cetera. So in a batch version, the way you would do this is you would come in, and the first row, you would basically calculate that, and then when you're done with the period, you would roll it up to just PC users, Mac users, male and female, and then roll it up to everyone. But let's consider what's going to happen in a real-time system if you wanted to maintain these real-time. So the data is coming in, and then every time a single record comes in that's PC male, you have to roll it up to the PC, and you have to roll it up to male. And so these would be kind of registers somewhere in your Hadoop ecosystem that would be constantly incrementing every time a new message comes in. And so rather than taking aggregate numbers and adding them up just once per period, every time a message comes in, you're going to be incrementing multiple registers. And we have technology for doing that in the MapR distribution. It's called MapRDB. But if you only do one increment per period, it's vastly more efficient than if you have to do many increments per period. So that's a case where, if you really, really need the data in real time, you can implement the real-time architecture, but it's going to cost you a lot more in resources. Okay, here's an example of something where it seems like you're getting real-time behavior, but it's really kind of a batch architecture behind it. And this is a product recommendation example. Where you go to a kind of a website for an e-commerce company, you see at the bottom of the page, you see recommendations for things you might be interested in, kind of based on kind of recent events that recent kind of browsing history on the website. And so the way this works is you have the user at the computer interacting with the web server, creating data, and then you're periodically rebuilding a data science model. Now, the periodicity you rebuild the model depends on a number of factors, but typically you're going to rebuild it every 5 minutes, every hour, every day, depending on how fast kind of user behavior is believed to change. And then the model is then dropped into the web server, and so when the user is actually getting the product recommendations, you're not going to the Hadoop Hadoop cluster at all, but the recommendations are done using a model which is batch produced that is present in the web server. And so there is in order to get these kind of product recommendations, it is not necessary to be using any of the real-time Hadoop technologies. Okay, so then you're left with a question, should I be using real-time architectures or not? And the takeaway from this is that you can often use real-time technologies. They are going to be more expensive in terms of resources available. Sometimes they don't make sense. Also, the batch tools are much more stable. They've been around a lot longer than the real-time tools, and you're likely to face fewer bugs. So given that, you can make decisions as to which components of your application should be real-time and which ones should be batch. Okay, So here are a few kind of architectures that have been proposed for doing real-time in the Hadoop ecosystem. The first one is the Lambda Architecture, where you have data coming in. The data forks to both a streaming and to a kind of batch processing. And then there is some aggregation or processing done, and then the process data is put into kind of a serving layer. And then the user or the automated system wishing the information can then pull from the batch layer or the serving layer as it sees fit. Now, a variant of this is the Kappa architecture, and by the way, the argument for a Lambda architecture, was actually not this question of whether you should do things in batch or real time, but the argument was that real-time architectures are kind of less reliable. They're more error prone, and that you should have a kind of batch architecture there as a backup. And so based on this, somebody came up with the idea of a Kappa architecture where you use a tool called Kafka, which basically batches up data as it's coming in. It streams it forward, but it holds onto it. And if you should discover that there was an error in your processing, you can replay the events going back. And so So it is a pure streaming architecture, but a pure streaming architecture that allows you, if you discovered you had an error, to go back in time and reprocess the data. And so this is making up for the perceived advantage of the Kappa architecture, which was that it could correct for errors in the real-time component. But of course, the Kappa architecture is a pure streaming architecture, and as we went through, as we discussed earlier, there are many kind of times when you don't want to use a streaming architecture. It doesn't give you any advantage, it may not work, and it may be a lot more expensive. And so something that we make use of a lot is what we call the mu architecture, where the data is coming in. There's still a batch mode, there's a streaming mode. Some applications are done batch, some are done streaming, but then we have a common serving layer. So the user does not have to know whether they are getting information through the streaming or the batch. It's all, the information they see is all combined, and they hit a single serving layer. One example of the mu architecture that we use at Think Big is the dashboard engine, which is for OLAP reporting. Events come in. Our streaming architecture is based on Spark, and we also have a batch aggregator. The aggregates are dumped in to MapR, time-based aggregates. And then we have an API that actually simulates SQL. And so you can connect tools like Tableau or MicroStrategy to it directly, and Tableau or MicroStrategy would send SQL to the API server, which would translate it into our storage format in MapR, and then it would send the data. And so if you had certain real-time metrics, those would flow in and be immediately available, and if you had batch metrics, there would be some delay, but they would be available kind of as soon as they were ready. Okay, one more example is something we call an event repository, and we have both batch and streaming versions of it that I kind of want to show you. So what is an event repository? Well, you have events from a number of different sources. They may be clickstream data, they may be ad click data, they may be call center data, or email marketing data. So the data comes in, and it's immediately sorted by user, and the colors are to represent kind of different channels that may have created the data. Data sorted in, and then you can look at each user and see what are all the events for that user that have occurred, for a given time period. So again, we have both batch and kind of real-time versions of it. In the batch version, the event sequences are stored in just plain old HDFS structures. When you want to process them, you use MapReduce or MapReduce-like operations to process them. It supports many kinds of analytics. I mean, most web analytics is batch. I mean, you can look at the last hour, but not the last second. And it's very, very efficient. Now, in a real-time version, the event sequences are stored in either MapR or HBase, keyed by the user ID, as we saw before. And there are kind of some other applications that we can support. We can support instantaneous, instantaneous metrics, like I mentioned before. If you wanted to know kind of how much product have we sold today up to the current moment, that can be supported. And it can also support kind of website personalization and real-time lookup. So if, for example, you walked in, you called the call center, which kind of has your phone number keyed to your user ID, then as soon as you call, the call center operator will see on the screen kind of what you just did on the website, just moments ago, and so they would be able to help you. Okay, so I just wanted to briefly show you kind of what we're doing at Think Big, where we have the kind of event repository over on the left, and then we have an increasing portfolio of components that query the event repository, can provide services in a kind of multi-channel event analytics environment. Okay, with that, I'm going to kind of pass the baton to Steve Wooledge, who is going to talk about some real-world applications that MapR has done employing some of these technologies.
Great. Thanks, Bill. It was a great overview. So as Bill said, I will talk about some specific examples and industry solutions that customers have deployed. So that'll get us into a little bit of what their architecture looks like. And I think what's interesting is they use a collection of different projects and technologies, such as Bill had walked through, like HBase or Hive or Storm or Spark. And it's this ecosystem that people build together that requires some thinking in terms of the architecture and how it's applied to the specific problem. So some quick background on MapR, the company. We're really focused on customers being able to create an as-it-happens business. And what we mean by that is making things more real-time, just like you have become more accustomed to on-demand TV or text messaging and other types of applications where you can just interact as needed. We believe that business and the enterprise needs to be able to operate in that same way. So not just analytics, but also taking action on things and doing things like recommendations or fraud detection and prevention, etc. We are a Hadoop distribution. We were founded in 2009. A quick history on Hadoop, if you're not familiar with it, was really popularized by Google with the publication of a paper in 2004, which inspired the Hadoop project, which Yahoo picked up to remain competitive with a lot of the things Google was doing on the storage and processing side around things like MapReduce. We took that same technology and thought about ways to make it more reliable and performant and broader in terms of supporting lots of different workloads in the data center for an enterprise. 2011, we launched the technology. We've been viewed as a leader in the space from a technical perspective. And a lot of the things we've been pushing the envelope on are around our NoSQL in Hadoop database called MapRDB, which is compliant with the HBase APIs, but provides better performance and some multi-tenant capabilities, which I'll talk about through some customer examples, and then extending that architecture to other workloads and applications, such as Elasticsearch, and being able to use search indexes for more real-time types of applications, but have it be synchronized with your data storage within the Hadoop infrastructure. And just a quick plug in terms of, and this might give you some information too, in terms of the landscape. Forrester Research is an industry firm that looks at different technologies, both the NoSQL key value database market, which is represented here on the left, is an area that we have the top ranked product in, as well as in the Hadoop distribution, which you see on the right-hand side. So what that means is the customers are getting a lot more value and real-time capabilities out of the platform for some of these use cases. Here's a list of companies that are doing things with Hadoop and MapR specifically. These are the public ones. We have a lot of other non-public customers. And what we typically see are people are on a journey. They start out looking at Hadoop for data storage and just offloading some systems or capturing new data that they would let kind of fall on the shop floor previously. Once they start to understand their first use case, they start to look for more things they want to do on it. We typically see customers double the size of their Hadoop infrastructure within the first 18 months. And 20% of our customers are now running over 50 applications on a single Hadoop cluster in their environment. And the point of that is that the Hadoop ecosystem and big data in general is very rich in terms of lots of different ecosystem projects and things that can happen. Once you get all the data into one location or this shared environment, it's about how can you support lots of different workloads. So people move typically from storage and batch processing to more real-time types of applications as they mature in their deployment. So one example of this hybrid ecosystem or architecture is some of the work that we've done with Teradata, specifically on integrating Hadoop into what's called the unified data architecture. So here you have data on the left, applications and users on the right, and having a data platform such as MapR that can ingest, transform, and store information and then feed downstream systems like the data warehouse or discovery platform for more advanced analytics, but also being able to support within MapR things like streaming applications or NoSQL database workloads, which I'll give you some examples of here on the next slide. So this is an example of how these systems interoperate it's not a rip or replace. People have invested a lot into their existing systems that provide a lot of value, and it's about how do you optimize the workloads across these different systems, but up the level of capabilities, particularly around real-time, is a thing that companies are continually trying to work towards. So the first example is a financial services company with an online investment portal, essentially for individual investors that want to look at different equities and bonds and things like that. And the overall goal, as you would expect for most consumer-facing applications, they want to improve customer engagement, customer loyalty. They want to reduce churn because there is a lot of churn in online brokerage types of companies. So by being able to provide better customer service and more relevant offers to the consumer, they can get better information and see more value. And in particular, one of the areas they wanted to do was connect their web portal with the call center, which Bill referenced earlier, and provide more real-time information to those call center agents to better serve the customers. So they had lots of different channels. They had implemented Hadoop, but were having some operational issues with uptime, and it wasn't something they were ready to roll into a 24/7 type of application. So we worked with them to replace that Hadoop distribution, to put in place more of a streaming type of architecture with the way that we can bring data into the MapR platform, and provide some real-time contextual offers both on the website using MapRDB or the HBase API, as well as a new application using Apache Storm that does some streaming aggregates and then loads that information into more of a CRM system, which I'll show on the next slide. So the results so far have been great. They've definitely increased engagement on the website, improved customer satisfaction, and the performance overall of the system has improved with much better reliability, where this is a system now they can run their business. So as I go through this, it's really a motley collection of a lot of different projects that they use to pull this off. On the right, they've got lots of different data points coming in from Teradata, which stores the customer information, call center records, web clickstream, which is coming out of Omniture, now Adobe, and then application logs from Splunk. And the first thing is with MapR, being able to support an NFS interface, or networked file system, that allows read-write capability in the data platform. Then using Hive to create a schema on top of that and materialize different customer attributes that a BI tool like Tableau or Datamirror can use then to generate reports. So a lot of the initial use case was to generate reports that people could use internally to understand who's clicking on what pages on the website. So this is more of a batch process, sort of phase one of the journey, but it gave them that insight to those different channels. The next phase of the project was to look at HBase, or MapRDB, as a store that could then serve content based on those key lookups that Bill was referring to earlier, and provide more relevant content on the website based on both the types, essentially segments that have been defined for these different customers, but looking at their behavioral attributes of what types of equities or different financial products they're looking at when they go to the website. So that's improved the content and the relevant experience on the web. And then the next phase was to take Apache Storm and take that stream of information that's coming in from the web, do some aggregates on it, and then load it into a real-time transactional system in the call center that allows the agent to look up your record and know what pages you've been looking at. So you may have gone into the site and started looking at bond funds as an example, and they could then recommend some other bond funds to you that maybe have a lower management fee or something like that on the website. So this is connecting across digital channels and improving the overall real-time response for customers. And then the next phase they're looking at is taking the Apache Drill project and providing more self-service exploration of that data on more real-time information, rather than going through that Hive batch upload into tables that then need to be created in reports. So that's one example. Another interesting customer example is Cisco Systems. They have lots of different business units. As you can imagine, as a huge multinational corporation, this is a view of their IT systems where they use a combination of different technologies, including Apache Hadoop, Teradata, and SAP HANA to serve different types of workloads across the organization. So taking anything from relational data out of the ERP or Salesforce.com, joining in clickstream, security information, sensor information from all the systems and the networks they provide for customers, and doing text analytics in the case of MapR, or doing more self-serve dashboards with SAP HANA, data exploration, real-time predictive, and then Teradata being used for more mission-critical financial reporting and operational reports. So it's really the shared infrastructure. And from a real-time perspective, one of the other groups within Cisco is their security division, which is using the MapR distribution to serve their customers from a SIEM, or security and information and event management, more real-time threat detection and prevention on the networks that Cisco runs for many of their customers. So there's lots of different examples of how companies are combining these motley crew, if you will, different types of applications and systems that are out there to solve business problems. Okay. Last example I'll give, this is a pure HBase application, if you will, is Urban Airship, which you may not have heard of the company. They're based up in Oregon, but they provide the messaging infrastructure to a lot of big sites like Starbucks, REI, Walgreens, ESPN. So if you get messages from any of your iPhone apps, many of them may be powered by Urban Airship, which is serving content out of HBase for advertisements and things like that. So Urban Airship was all about building that one-to-one brand relationship for their customers' customers through push messaging and geolocation targeting. Lots of different customers need to be supported in this environment, and one of the things they were challenged with is, with traditional Hadoop, they had to create separate application clusters to support different workloads because there wasn't a very good way of doing data separation and resource management and isolation. With MapR, they were able to use our HBase implementation and consolidate their clusters from 8 clusters down to 1, which reduced their hardware footprint enormously while maintaining good SLAs and this real-time delivery infrastructure that HBase provides. So you can see some of the applications and messaging things within the iPhone or Android apps here with Walgreens, REI, and Starbucks as examples. So again, a pure messaging, real-time delivery mechanism run by Apache HBase. Again, I just wanted to highlight for folks, the open source ecosystem is very vibrant. There's lots of projects, and literally every week there's some new project that gets spun up and put out there. And as a technology vendor, what MapR is really focused on is bringing the best of all these worlds together on a mission-critical, reliable platform for our customers. So we support multiple projects like Spark, multiple SQL engines like Drill, Spark SQL, Impala, Hive, and it's really about providing choice for the customers. And if they want to do real-time streaming, they can use Spark Streaming or Storm. If they want to do HBase applications, that's supportive. And there's lots of different things within this. But the thing that's different about MapR is that we've done a lot to architect the data platform to make it more reliable and more scalable. So we've eliminated the name node as an example, which allows us to scale the file count to trillions of files, which is a 5,000 times higher scale factor than you would get with HDFS, which means you get a lot less footprint in the data center, and the performance improves tremendously with what we've done. So 2 to 7x faster in terms of performance across all these different workloads. 30 to 50% less hardware is what we typically see in overall total cost of ownership. And we've integrated in enterprise-class storage mechanisms like mirroring, point-in-time consistent snapshots, high availability, rollback. We've got a table replication mechanism for MapRDB, which allows you to have multi-data center, global distributed applications that are synchronized. So you can have local data centers that provide that real-time workload and then synchronize to have the latest data across different data centers. So very global in terms of scope, which is really what MapRDB is about. And everything within the Apache Hadoop and other open source packages inherent all the goodness of this platform in terms of reliability, performance, and the ability to have read-write access to the file system itself. So that's really what we deliver underneath of all this for our customers so they can take advantage of the Hadoop ecosystem, the innovation that's happening there, but also run it in their data center with more reliability. So with that, that's the quick overview I wanted to append, I guess, to the great information that Bill shared earlier. And to kind of summarize, and we'll open up for Q&A, real-time is great, but there's also some trade-offs. So know when you need it. You may not always need it. And there's lots of different tools and workloads out there, whether it's a relational database, NoSQL database, the Spark environment, the Hadoop environment. There's lots of different tools to solve the job. There's more information here if you want to get it on the Think Big dashboard engine, which I think is a really cool real-time OLAP engine. And if you just want more information on Hadoop in general, we've invested in some online on-demand Hadoop training, which is completely free. And we just rolled out some new HBase developer and administration sessions that you can view for free and work towards your certification as a Hadoop application developer or administrator. And there's always product you can download for free and get started on, together with tutorials and other types of things to get your head around all the different applications that are out there. So with that, I'll turn things back to Bill, our host, to open up any questions that people might have.
Well, Steve, Bill, thanks so much for that excellent presentation. And let's get started with today's Q&A session. And I do want to thank the audience for their participation, as we've had a lot of questions that have come in during the presentation, and we'll do our best to get through all of them in the time remaining. So during this Q&A session, I'll leave up this screen with contact information if you'd like to contact either of our presenters following today's webinar. So let's get started. Bill, back on slide 28, 29, and 30, you talked about the Lambda, Kappa, and Mu architecture, and you described the Mu case as powering OLAP and the dashboard. We had some questions come in, though, if you could give some case examples for using the Lambda and Kappa architecture.
Okay, let me go back to the slide. So the now anything that you could do with the Mu architecture, you can do with the Lambda architecture is just kind of more. There's kind of more technology and kind of more work, and you'll require more resources. So the basic idea that the Lambda architecture introduced is that you should have separate batch and streaming kind of data flows. Now, the reason it was introduced was, we believe, kind of the wrong reason, because streaming is inherently unreliable. But nevertheless, that was the reason it was introduced. But once it's there, you can use it for different purposes. So let's say you wanted to do kind of some kind of OLAP or aggregate kind of engine using the Lambda architecture. So you divide your metrics into the ones that you want to do streaming and the ones you want to do batch. And then you have two entirely separate serving platforms for the aggregate data. And then the user or the technology that's sitting on their browser has to know kind of which serving layer to go to for which for which result, and you need two serving layers. It's kind of not really necessary. So in the Mu architecture, it's kind of exactly the same, but you have a single serving layer. And for what we do, the serving layer is MapR DB or HBase, and they work largely the same way. And the user simply hits a single kind of MapR DB or HBase instance, pulling out aggregates, and they don't have to know whether that aggregate was kind of came through the streaming or through the batch kind of flow.
Oh, Bill, thanks very much. And in that same vein, one of our viewers asked if your discovery platform was the same or similar to the concept of a data lake.
Yeah, well, data lake is a term that gets applied to a Hadoop installation where data coming in is kind of well managed. So there are governed ingestion kind of processes where at any time you can look and find out which data has brought in. Security is well managed. So it's basically the difference between a data lake and a data swamp is a data lake you can look in and you can find out what's there. You know it's being well managed and it's inherently secure.
Yeah, people really need to take to heart that lesson about data swamps. You know, this question frequently comes up, and one of you can address the issue. What is the difference between HBase and the MapR database?
Yeah, I can take a stab at that. I think Bill also has a lot of hands-on experience there. I mean, the goal was to, let me give some history, I guess. From our customers, one of the things we saw was that there was a lot of support calls around HBase historically, and the community's done a lot to improve things. But given that HBase runs in a JVM on top of HDFS, which is a JVM on top of the Linux file system, there's a lot of layers of work that often needs to happen as you're writing commits back to the database. And so HBase typically has these compaction cycles that can impact operations if you need to be running that application in a 24/7 type of environment. So with MapRDB, we wanted to expose the HBase API, but do it in a way that takes advantage of our read-write file system in our distribution so that you can essentially eliminate compactions and have this distributed consistency, which is very difficult to do at scale. So typically what we see is around a 5 to 7x improvement in performance of HBase applications that run on MapRDB with much better throughput, lower latency, and the ability then to run those HBase applications directly on the same shared data lake infrastructure where you have other workloads in your Hadoop environment running. So that's kind of the high level on the differences, and there's a lot of information and tutorials and things like that people can play around with it. I don't know, Bill, if you have any other insights based on some of the things we've been doing together on the dashboard engine.
I think you covered it pretty well, Steve.
Yeah. Well, that was a great answer, and thanks. I know that's a complex topic, and a lot of people are wondering about that. Let me put the email addresses back up. And in that same vein, a question comes, are there any SQL Server, APS, Azure, or HD Insight case studies with MapR integration?
Let's see, HD Insight, Azure. So we've just started a partnership with Microsoft. I want to say we have our first couple customers up on Azure now. I'm not 100% sure on that, but I know we've been working together with them on the engineering side to put MapR up into their cloud, as well as we've been OEM'd, if you will, within EMR from AWS for a long time, as well as Google Compute. So there's we do have a lot of customers that do run in cloud environments. Microsoft is a fairly new partnership for us, but there's a lot of effort going into that right now.
Great. And early in the session, we had one obviously frustrated user who asked, we have a few Oracle batch jobs using their DBMS scheduler, and they run for hours. Would it be possible to convert these jobs into Hadoop analytic jobs and gain performance benefit?
The answer is likely. I mean, we would have to know more about what these jobs do, but frequently when Think Big is a consulting firm, and we are often brought into situations precisely with that description where there are batch jobs being run on Oracle, and typically we come in when there are daily batch jobs, and the daily batch job is getting longer and longer and longer, and as soon as it exceeds 24 hours, then nothing works anymore, and typically we don't just take the SQL that was being run on Oracle and run it on kind of run it on Hadoop, there is some kind of redesign of the application. But typically in a Hadoop environment, what would be a 15 or 16 or 18-hour kind of Oracle job the work can be completed in under an hour.
That would be amazing, and I'm sure that viewer would be very happy to have that time savings. And while we're on the topic, Spark, streaming, or Storm, which do you pick? What's better for real time?
They're kind of different. What Spark streaming does is basically Spark has a concept of an RDD, which is a description of the thing it's about to execute, and before it executes it. And if you should have a failure, then you can go back to the RDD and sort of re-execute it, and that's how it achieves its reliability. Storm does not have built-in reliability in that way. So if you have a node failing in a Hadoop your Hadoop cluster, then whatever kind of Storm job is being run on that node, the information would be lost. What people typically do with Storm is they run a kind of Kafka in front of the Storm topology. And so if you should have a failure, then you can kind of back up your events and kind of reprocess them. Spark has the reliability built in. It's also very elegant. If you are doing kind of machine learning or you're doing graph processing, there are some very nice libraries that come with Spark, and you can do everything kind of in one environment. Storm has been around longer. It's kind of it's used in a lot of production systems, and you program in Java. The Java is the kind of native language of Storm, where in Spark you'll kind of have to learn a bunch of new tools. So both of them work. But if you kind of go with Spark, you're going to have kind of all your processing kind of be in one infrastructure in one language.
Great. Oh, thanks, and especially for adding the clarification about Kafka, which I think we were all interested in having reinforced. Question comes. You had a diagram of an architecture in which the data stream fed both a batch process and a real-time process, and the viewers are wondering whether or not that creates a reconciliation problem or a redundancy problem. What happens? Is it possible that the users will get two inconsistent results from the two separate systems?
That's a very good question, and I think that was the idea behind the original Lambda architecture, where you have the different flows, because the streaming was viewed as being unreliable, and so the batch was basically the backup for it. Things have evolved since then, and streaming architectures can be quite reliable. As I said, you can either kind of use Storm or Storm with Kafka, or you can use Spark. And so the main reason we believe now for having both batch and stream is certain applications are simply better with streaming, certain are better with batch, and you're running different applications. So you're not going to have a problem with reconciliation because they are doing different things. You don't have the batch duplicating what the streaming is doing.
Excellent. Excellent. Well, a lot of questions have come in, and Steve and Bill, thanks for some great answers to some very good questions from our audience. For those of you who asked questions today that weren't answered today, we'll be sending all the unanswered questions to both Steve and Bill and the MapR and Think Big team so they can follow up with you after today's webinar. I do have just a couple of final announcements. First of all, if you'd please mark your calendars for September 15th, that's our next Data Science Central webinar, which is 5 Things Your Organization Needs to Succeed in Data Science, sponsored by Teradata. Also, today's taping will be available for on-demand viewing later today, and you can find it on the home page of datasciencecentral.com in the webinar tab located at the top of the page. Well, that brings today's webinar to a close, And I'd like to thank our audience for their attendance and thoughtful questions. And a special thanks again to MapR and Think Big for their sponsorship, and our speakers today, Steve Wooledge and Bill Kornfeld, for their insights on today's topic. My name is Bill Voorhees. I'm very pleased to have been your host for today's event, and I look forward to seeing you all again on September 15th. Have a great day.